Alright, grade 11 chemistry. We're talking about displacement reactions today. So that's single displacement and double displacement reactions. And the point of today's lesson is really that it's very easy to spot and figure out what's going to happen in a single or a double displacement because, they're just going to switch. And we already know the ions and everything. But the challenge is predicting if they will actually be spontaneous or not. That's what we're talking about today. Here's what we're going to talk about. We're going to predict some single displacement reactions. Then we're going to do a bunch of double displacement stuff. We'll learn about the three common classes of double displacement reaction. Those are the precipitation reaction, neutralization reaction, and the gas evolution reaction. Then I'm going to spend some time doing practice problems on single and double displacement reactions, and that way you guys can get used to the kind of tools and thinking that we're going to need for solving these problems. So what do I mean by predicting whether they will be spontaneous? Right, predicting whether they'll be spontaneous. Well, typically these chemical reactions only go one way. Right, they'll only go one way. And a prime example of that is this thermite reaction. So it's a single displacement of iron oxide and the iron oxide and aluminum. Classic single displacement, right? The aluminum is going to displace the iron, taking its place with the oxygen, and the iron is going to be alone. Here's the reaction in action. The link to this video is down below. Please watch it. But here comes the video.
Wow, oh, okay. Oh, wow.
Yep.
Oh, wow, okay.
And out the bottom comes liquid iron.
Liquid iron.
That's liquid that's
That is
dropping into
liquid
the
metal.
sand.
Falling down into the sand.
How hot is that?
It's in excess of 4,000 to 5,000 degrees Fahrenheit.
Wow. So that's like molten, right?
That is molten.
Ooh.
In fact, if you want to try to sneak around the side,
Oh, I would love to sneak while something's just, flaming.
you'll be okay.
Okay.
Just reach down in
Oh,
there,
boy. Uh-huh.
pick that up, and just hold it up in the air so
Yep.
the camera can get a good shot of that.
Sure.
Of course, don't drop it on my tablecloth because it will
Okay.
ignite the tablecloth.
Sure, that would be good.
Okay, so there you go. That is the thermite reaction. That is how you actually join railroad tracks together if you need to out in the field.
Yeah.
You do this reaction around the ends of the tracks, join them together with a blob of...
Oh.
So you can see the reaction happening here, right? It's making a bunch of energy. A bunch of energy is getting released. And so a lot of energy gets released when it reacts, which means that the opposite reaction would need to put in a lot of energy for the opposite reaction to work. And that's probably not going to happen. This is like, if I burned a piece of paper and I released a bunch of energy from my piece of paper, and then I would have to try to unburn my piece of paper. I'd have to put in a bunch of energy and unburn it. Of course, trees do that, right? They take the sun and they make wood from CO2 and H2O, but it takes energy and time. So this is what we mean by spontaneous. The forward reaction is clearly spontaneous. It very quickly happens. The reverse reaction is not. So the reverse reaction would not proceed. So when we have something written like this, we can't just assume that they're going to swap. The iron is not going to displace the aluminum because the aluminum, when it displaces the iron, releases the energy. Going the other way, not going to do anything. So how do we figure it out? How do we figure out that the aluminum will replace the iron, but the iron won't replace the aluminum? Well, someone else did all the work for us, right? Someone else did all the work for us. And this is called an activity series. So this is the nice thing about chemistry is people do a bunch of experiments, they relate their experiments, the answers of their experiments, and then you can make these tables and be like, oh look, the pattern is, aluminum will always replace iron. Aluminum will always displace iron. So here's an activity series. Here it is. Note, keep in mind here, it's based on the single metal, not the one that's already been bonded. So if we want to prove that aluminum will replace iron, aluminum should be higher up than iron in the table. And when we look at it, here's aluminum, right there, aluminum. Notice solid aluminum. And it's higher up than iron. So the aluminum will replace the iron. It has a higher activity than the iron. So that predicts that it will be that will be an effective replacement. If you're trying to go the other way, the iron is lower than the aluminum, so it can't displace it. You can almost think of this as almost like a power level for these metals, like who's the bigger bully. Lithium will replace absolutely anything. Meanwhile, gold it won't replace anything. It's not very likely to replace anything. This is why gold tends to stay as solid gold and doesn't really react. Same with platinum and silver and copper and stuff, right? One interesting note here is that hydrogen is right here. That would be hydrogen as an acid. So hydrogen will actually, everything above this line will react with acids. Everything below it won't. Hydrogen in water will react with some of these things as well. Basically everything up above sodium will react with water. So that's kind of neat. So one classic example of this is dissolving pennies. Excuse me. Pennies are zinc, mostly zinc, but it's plated in copper. So what you can do is put pennies in hydrochloric acid. Pennies into hydrochloric acid. And we can look at our list here and to see if the zinc will displace the hydrogen or the copper will displace the hydrogen. So we predict what'll happen. So what the prediction here is that here's the hydrogen. Look at zinc. Zinc is higher up the list. It's got a stronger activity than hydrogen does, right? Zinc stronger than hydrogen. So that tells us that the zinc can bully hydrogen out of the way. The zinc can push the hydrogen out of the way. And this will proceed. Zinc will proceed. But copper has a lower activity, right? A lower activity than hydrogen. It's not as strong as hydrogen. It can't push hydrogen out of the way and take its place. So the top reaction will proceed. The bottom reaction will not proceed as written. So it's not as simple as just predicting the products. You also have to predict whether those products are reasonable, whether they're going to work with an activity series. And I'm going to find a video of that penny experiment and I'll show it off. So here's a video of that exact experiment, penny and HCl. And you can see that down below in the description. But note that there's bubbling coming off of this penny, but not this penny. Basically, this penny, they kind of grabbed, took some sandpaper and they rubbed off some of the copper to get at the zinc underneath. And then over time, note that that penny is now floating, but that penny isn't. And they're going to clean it off. Clean it off.
That is,
And what you get,
it's flat. Is just a regular penny. This is the activity series.
here's the activity series, and they'll tell you.
And as you can see, zinc is more active than copper.
Hold on. And that penny, what happened was the zinc actually came out of the inside of it. So you get basically a hollow penny. I'm going to stop that. Yeah, a hollow penny. See how it's actually been completely taken out. So the zinc came out of the center of the penny. Let's find that video again. Yeah, there we go. So the zinc came out of the center of the penny, but the copper shell has remained. And we predicted that. We predicted that the copper wouldn't dissolve, but the zinc will. So yeah, classic chemistry experiment that normally we do in class, but can't do it in class. Yeah. So how do you figure this stuff out? Well, you write out the single displacement reaction, pretending it actually happens. And then you identify what's trying to do the displacing. Here, zinc is trying to displace hydrogen. So zinc is going to be a bully and try to bully hydrogen out of the way. And then you look in your table. Zinc is stronger than hydrogen, so zinc can bully hydrogen out of the way and take its place. And that's how you figure out single displacement reactions. Next, we're going to talk about double displacement reactions. So I'm going to pause and fix up my stuff here. All right, double displacement. The big thing about double displacement is the keep in mind up here, it's going to stay up there, is that once the ions are dissolved in water, they are absolutely free to move. If you dissolve salt in water, sodium chloride into water, the sodium and the chlorine are just now all over the place in the water. They're free to go. Sometimes they'll get back together, and then they'll very quickly get ripped right back apart, and so on. So that's the concept, and all of our double displacements are going to happen in aqueous environments. Right, aqueous environments. They're free to move wherever they want. If I dissolve salt in water, when I write NaCl aqueous, what I really mean is sodium aqueous and chlorine aqueous, and they're just moving around. And they'll bump into each other, but the water very quickly just pulls them right back apart. If we dissolve more than one thing in the water, the same thing can happen, right? If I dissolve, say, sodium chloride and potassium bromide in water, I'll get sodium, chlorine, potassium, and bromine in my water. And they're just all floating around now, right? We've got 4 species floating around in our water. And the sodium might get close to a potassium, and then they'll go away from each other because they're both positively charged. Chlorine might get near bromine, and they'll go away from each other because they're both negatively charged. But sodium might get near, say, bromine, right? The sodium might get near the bromine, and they're negative. They're positive and negative. They'll get stuck together, but then very quickly the water will rip them right apart. Or the potassium might get near the chlorine, positive and negative, but then very quickly the water will rip them right apart. There's no real reason for them to recombine. And they're always bumping into each other. There's lots of them all over the place. There's billions of them. No reaction actually occurs usually, unless something happens. Unless 2 of those ions can come together and form something the water can't pull apart. Right? If the 2 ions come together and make something the water is too weak to pull apart, that might be one thing that happens. Or they might come together and make water, and then water won't pull it apart because it's water. Or, you might make a gas. So these are the 3 ways to get things out of solution. You can make something that's insoluble. Insoluble means held together so strong that the water can't pull it apart. You could create water, H2O. Or you can create a gas. If you have 2 things that meet each other in such a way that they react and make a gas, then the gas is going to leave the water and you're going to get a reaction. We're going to go through each one in turn. So, those are our next 3 things: precipitation, neutralization, and gas evolution. So first off, precipitation. This is called a precipitation reaction. What we're making is a solid, something solid. Right? So what you do here is you can mix silver nitrate, which is silver and nitrate are both soluble in water, and sodium chloride, which clearly soluble in water. But then when we mix them, right, everything's bumping around, and the silver can bump into the chloride. And when the silver bumps a chloride, now they're stuck together. The water is too weak to pull them apart, and they stay there. And it turns into a solid, because now they can clump together and make a lattice and make a crystal, and then those are going to fall out of solution. I'll find a video of that happening, actually. Right, here's a super quick video of that. This is silver nitrate. I put it in, notice the solid instantly, basically. It looks like it's instant, but it does take time for the ions to bump into each other. There's just a lot of them, so they're hitting each other very quickly. And that's a double displacement reaction. And then they're just showing that when they get together, now they're stuck together. So I'm going to keep that down below. And then they're creating now a new crystal, right? The crystal just starts growing, and that's what we're seeing. That's what we're seeing when it precipitates. So yeah, find that video down below. Yeah. So if something's insoluble, if 2 ions get together and they're so strong that water can't pull them apart, you get a precipitation reaction. How do we know that something is soluble? Well, hey, it's chemistry, right? It's based on empiricism. Someone did all the work. Other scientists painstakingly reacted a bunch of different things and then figured out, hey, this is soluble, this isn't soluble, this is soluble, this is soluble. And they make this. This is a solubility table. Notice you've got cations on top, anions on the side, and these are the combinations of the different cations and anions. So if we go back to this reaction, right, silver nitrate and sodium chloride, when we look at it, the silver, right, the silver nitrate is soluble. Sodium and chlorine, when those 2 ions bump into each other, soluble. When the sodium bumps into nitrate, no problem, because we've got silver, nitrate, sodium, and chloride in our solution. But when the silver over here, bumps into the chloride, when the silver bumps into the chloride, now they're stuck together too strong, water can't pull them apart. It's insoluble. There's also these slightly soluble ones around, and then some blank spaces where I guess the reaction is weird or does something strange, and other stuff happens. So yeah, that's solubility table. Someone did all the work and we just used their table. Here's another type of table where it's just general solubility rules. So one of them is all nitrates are soluble. Well, yeah, here's nitrate. All of them are soluble. All acetates are soluble. Silver acetate is slightly soluble, it says. This one says it's soluble. And various other things like that. So you have two kinds of things. You have general rules and you have these kinds of rules. Typically, smaller ions are more soluble, so you note that the alkali metals are very soluble, and the halogen ions are very soluble with a lot of different things. And the bigger the charge, the less likely water is to be able to pull them apart. So you get these insoluble, heavier ions, heavier metal ions. So to predict this, it's pretty straightforward. You identify what the ions are, and then you just look in your table for all of the different combinations of your different ions. You have to look at all the different combinations. Because once again, if you look up here, once the ions are dissolved in water, they are free to move. And we combine the two solutions, all of the ions are now going to mix and match and mingle. And if two of them mingle and that combination is insoluble, you're going to get precipitation. Okay, part 2 is neutralization. So I'm going to pause. Yeah, so neutralization reactions are the next one. This can only be done in a double displacement if you've got hydrogen on one side and hydroxide on the other. So hydrogen on one side and hydroxide on the other. Hydrogen is a positive, so it's always going to be at the front of a molecule. So acids make H+, so HCl, H2SO4, things like that. Bases have this hydroxide. They're always going to be at the end, OH, OH. So when you see an H on the front and an OH at the end, you'll know that that double displacement can come together and make water. So that is two ions, H+ and OH, but when they get together, they make a molecular compound, which is water. And then the water will just join the rest of the water in your aqueous solution. It'll just, disperse. So it's a neutralization reaction because it's an acid and a base canceling each other out, is why we call it a neutralization reaction. To recognize it, you just have to have an H+ on the start of one and an OH- on the end of the other. And it produces liquid H2O, that just joins the rest of the water. Remember, they just bump into each other. And a salt. So a salt is something that's produced from a neutralization reaction. So it doesn't necessarily have to be sodium chloride. A salt is literally anything produced from neutralization. So here HCl and KOH, if we mix HCl, this is the acid, the H, and KOH, which is the base, the OH, the H and the OH meet and they'll make water. And then that leaves the potassium and the chlorine still just floating around the solution, right? So you've just got potassium and chlorine floating around in the solution. So that's a neutralization reaction. Last one here is gas evolution reactions. Right, gas evolution reactions, it's kind of a cool name, gas evolution. You're creating a gas. So sometimes you can make a gas, and typically the only two we're going to talk about are CO2 and NH3, so CO2 gas or ammonia gas. And that's going to be a decomposition of carbonic acid, which is H2CO3, or ammonium hydroxide, which is NH4OH. Here are carbonic acid and ammonium hydroxide. So carbonic acid comes from any acid, H+, meeting a carbonate. It can be a carbonate or a bicarbonate. So when H+ meets CO3 or H+ meets HCO3, you make this, H2CO3. Now that very quickly in water will decompose to CO2 and H2O. Most of it will decompose. Some of it will stick around, but most of it will decompose. And then the CO2 is a gas, which is not going to stick around in your solution, and out it goes. It'll bubble out. This is, for example, what we see with the vinegar and baking soda reaction. Vinegar and baking soda reaction is vinegar has the acid part, it brings the H+. Baking soda has the bicarbonate, HCO3. It very quickly makes H2CO3 in a double displacement, and then the H2CO3 very quickly decomposes into CO2 plus H2O. But it feels instant. It looks instant. Ammonium hydroxide is a different one that you can do. If you have an ammonium compound and a hydroxide compound, so something with ammonia and a base of some sort, they'll get together and make this stuff, NH4OH. And same thing happens. It very quickly decomposes into water and ammonia. The ammonia is a gas, and it bubbles out, and it smells really bad. Certain cleaning products will react like this when they touch a base, and then it smells awful. How to recognize it? Well, you just need H plus on one reacted, and for a CO2 formation, you need to make carbonic acid. So what you can do is just do a double displacement, and if you've made carbonic acid, you know that the carbonic acid will decompose. Or if you make ammonium hydroxide, you know that the ammonium hydroxide will decompose. And I'm noticing here that my my screen is cutting off, so let me, there we go. And I'll just take away the current topic for a second. So we write these in one step because the decomposition happens immediately as soon as the ions touch each other, and out they go. So here's an acid, the H meeting the carbonate, CO3. That's going to make H2CO3. And then that H2CO3 will decompose perfectly into CO2 and H2O. So we skip the decomposition step. You can write it in if you want, but typically we'll skip it. Same with calcium hydroxide here and ammonium chloride. The hydroxide will meet the ammonium. It will make NH3 and H2O. H3 and H2O. That should make actually 2 H2O. That should be a 2 there. There should be a 2 to balance the H2O. Sorry about that. And the remaining ones are the calcium and the chlorine. Calcium chloride to make calcium chloride. So that's just a memory work thing. You just have to remember that that's going to happen. And that's the end. So let's review what we talked about. We predicted some single displacement reactions with the activity series. We predicted some double displacement reactions in terms of solubility, in terms of an acid meeting a base, and in terms of creating a gas. And the gas was just if we made H2CO3 or if we made NH4OH. Now I'm going to spend a little bit of time, maybe 5 minutes or so, doing some practice problems out of the textbook. So stay with me for some practice problems. Yeah, let's do some practice problems. Here's one about single displacement reactions. It says, use the activity series to predict whether each of these reactions occurs. Write a balanced chemical equation for each reaction that does occur. No reaction for those that do not. So on the other screen, I've just got my activity series, so I can skip back and forth. So first one, ALS plus AgNO3. ALS plus AgNO3. Let's have a look at it. ALS plus AgNO3. So our question here is, what is trying to displace what? Well, the aluminum wants to displace the silver, right? The aluminum wants to displace the silver. Can aluminum displace silver? Well, it means that aluminum has to be stronger than silver in order to displace it, because that's what's trying to happen here. When we look over here, let's find that. Aluminum is here. Silver is way down here. Yes, aluminum is much stronger than silver. So when we look at it here then, yes, this will react. Yes. Yes, it will. So what will it make? Well, the aluminum is going to make an aluminum 3+. Silver, the nitrate is an NO3-. I just get that from this table of ions here, right? So I'm going to need 3 of these to match 1 aluminum. That's AlNO3 3 plus, and then the silver is going to end up by itself, just silver. That's going to be solid silver. That's going to be aqueous, probably, because all nitrates are soluble. And now we have to balance it. Let's balance this thing. Well, we have 3 NO3s, so we'll need 3 of these. And now we have 3 silvers because we multiplied everything by 3. So 3. Now it's balanced. So that's our first one. Let's have a look at our second one. Second one, we'll just get all these together. Zinc and lead nitrate. Zinc and lead nitrate. Zinc plus lead nitrate. Right, so what's trying to displace? Well, the zinc wants to displace the lead. Will that happen? It means the zinc needs to be stronger than the lead in order for this to occur. So let's look at it. Zinc is here. Lead is here. Yes, zinc will replace lead. So yes, that does occur. Yes, zinc will displace lead. So zinc will displace lead. This will occur as a reaction. Zinc makes a 2+, so it'll take 2 nitrates. I just get that from the table, right? Zinc is here, it makes a 2+. That'll be zinc, nitrate, like that, because it takes 2 nitrates for 1 zinc, plus just lead by itself. So solid lead, zinc nitrate, aqueous, and it will displace. It will displace. And this is balanced already. 1 zinc, 1 zinc, 1 lead, 1 lead, 2 nitrates, 2 nitrates. We're good to go. Look at the next one. Gold plus water. Gold plus water. So let's see if gold will displace water. In order for gold to displace water, gold needs to be stronger than water. Right? Gold needs to be stronger than water. Stronger than hydrogen, I should say. And when we look at this, gold is way down at the bottom. It is the weakest one. So no, it's not going to displace the hydrogen in the water. And in fact, it has to be stronger than that. It has to be up around here to displace the hydrogen. So no reaction. So this is a nope. That doesn't happen. So nope, no reaction. Nothing to predict because it won't happen. It will not happen. I'm going to set up for some double displacement reactions. So for double displacement, here's some practice problems. Will a precipitate form when the following solutions are combined? If you predict that it will form, write the balanced chemical equation. Includes states. If you predict no reaction, write no reaction. So here's our 5 things that we're going to predict. We're going to go through them bit by bit. So let's look at silver nitrate plus potassium sulfate. Silver nitrate plus potassium sulfate. Right, first things first, this is going to be a double displacement. They'll start aqueous because they're going to be soluble. I'm going to split them up, right? We're going to split them up into their ions. Silver and nitrate and potassium and sulfate. Now we have to check whether all of these are actually going to react together, or if any of them are going to be insoluble. We don't need to check silver nitrate because we know it's already soluble. We don't need to check potassium sulfate because we know it's already soluble. But what we're going to check is silver sulfate, if the silver gets with the sulfate, and we're going to check potassium nitrate to see if either of those is insoluble, because if they are, we're going to get a precipitate. So let's have a look. We're checking silver sulfate. Silver, here's sulfate. We get a slightly soluble, which means you'll probably get a precipitate. Let's just check the other one, which was potassium nitrate. Potassium nitrate, that is soluble. Soluble. So when we look here, this is soluble. This one is not soluble. So that guy, when the silver meets the sulfate, the bond is too strong, water won't pull it apart, you get a solid coming out of solution. So yes, this will react. It will produce silver sulfate, but we have to do our ions. So silver sulfate, silver +1, sulfate -2. You get that from our table of ions. We need 2 silvers for every sulfate, so it's going to be Ag2SO4. And here's the state symbol, right? This is the one that's insoluble, so it's going to be solid. It's going to be solid. And then the other one, the potassium nitrate, potassium does a +1, nitrate does a -1. That's fine as is, so potassium nitrate. That one's soluble, so it's going to stay aqueous. The potassium and the nitrate are just going to be floating around. No problem. All right, let's go to the next question. So this would be the answer here. Oh, we have to balance it. Right. We have 2 potassiums, but only 1 potassium. We're going to double that up. Now we have 2 nitrates, because we multiply the whole thing by 2. 2 nitrates. We only have 1 nitrate here, so I need 2 silvers. And those 2 silver nitrates, the 2 silvers, will balance my 2 silvers over here, so we're good. Let's try the next one and see if we get a reaction on the next one. The next one is ammonium chloride. Ammonium chloride, NH4Cl plus Na2S. Right? Will this react? Well, what we have to do is break it up into our individual ions. So this is aqueous, Right? What'll happen? Well, split it up into our individual ions. The ammonium and the chloride are compatible. That's fine. The water will pull it apart and they'll just float freely. Sodium and the sulfide will float freely around. What happens though if they mix, right? All 4 of them are now floating around and mingling. Well, the ammonium might get with the sulfide. The ammonium might bump into sulfide. Let's see what happens when ammonium bumps into sulfide. And then the sodium might bump into chlorine or chloride, and we'll see what happens there. I think we can probably tell that this one's going to be soluble. That's fine. We're going to check our ammonium sulfide. So let's go back over here. Ammonium sulfide, here's ammonium, and sulfide, yeah, we're fine. Ammonium sulfide, soluble. So both of these are soluble. Both of them are soluble. Soluble. And if they're soluble, it means they're going to stay in solution. They're just going to keep floating around. Ammonium is going to meet sulfide and just be like, oh, hey, what's up? How'd they go? So this will have no reaction. We predict no reaction. It'll just look like we pour 2 liquids together and nothing happens because they're both soluble. Everything stays soluble. So that is double displacement that doesn't do any reaction. If I ask you to predict this one, that's the answer. They don't switch. They don't swap. Because there's nothing making them stay together. Yeah, that's it. I'll leave the rest of them as a kind of an exercise for you guys. We'll take them up in class tomorrow. Now we have the tools to predict most of our reactions. Combustion reactions are coming up. That's going to be fun. See you guys in class.